Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I will explain you the eigenvalues and eigenvectors and its properties. Let me go to the presentation. First, I will define the eigenvalues and eigenvectors. Let A be n cross n matrix. A scalar value lambda is called an eigenvalue of A and the vector x is called the eigenvector of A, which is corresponding to the respective eigenvalue lambda. The non-zero vector x is such that it is given as Ax equal to lambda x, where x is the eigenvector, A is the given matrix, and lambda is the lambda or the eigenvalues. Which is simplified as A minus lambda I into x equal to 0, where I is the identity matrix in which the principal diagonal elements are unity. X is the eigenvector, lambda are the eigenvalues. First, I will define the steps to find the eigenvalues and to find the eigenvectors. Eigenvalues can be represented as lambda I, where I equal to 1, 2, 3 up to n. For n cross n matrix, there will be n eigenvalues. For 2 cross 2 matrix, there will be 2 eigenvalues, lambda 1 and lambda 2. For 3 cross 3 matrix, there will be 3 eigenvalues, lambda 1, lambda 2 and lambda 3, like that. So, first I will define. First step is to find the matrix A minus lambda I from the given matrix, and then next step is to find the determinant of the matrix A minus lambda I, and then to find the characteristic equation which is represented as A minus determinant of A minus lambda I equal to 0. Okay, so these are the steps to find the eigenvalues lambda I, where I equal to 1, 2, 3 up to n. Next one is steps to find the eigenvectors. After finding the eigenvalues, we can find the eigenvectors for each eigenvalue. So if we are having 3 eigenvalues, means there will be 3 eigenvectors, like that. So for each eigenvalue lambda 1, lambda 2 up to lambda n, we need to find the eigenvector. We need to find the equations first. A minus lambda I into x equal to 0, where x is the eigenvector, and to solve the equations A minus lambda I x equal to 0. Solve the equations to find the eigenvectors x, which is represented as x1, x2 up to xn, or the unknown variables of the eigenvector. We need to find the eigenvector for each eigenvalue. So there will be n eigenvectors and there will be n eigenvalues for n cross n matrix. If it is a 2 cross 2 matrix, means there will be 2 eigenvalues, and for each eigenvalue we will be having eigenvector. So there will be 2 eigenvectors, like that. So I will explain you with one example problem. Here I have given 3 cross 3 matrix. I am going to find the eigenvalues and then to find the eigenvectors. First I will find the eigenvalues. So what are the steps? A minus lambda I. Lambda is the constant term, lambda into I. I is the identity matrix which has the value of 1 at the principal diagonal elements only. So we can consider only the principal diagonal elements. Here we are having the elements as 1, 5, 1 or the principal diagonal elements. So we can include the lambda in that elements only. So like that, A minus lambda I equal to 1 minus lambda. So we are including the lambda in the principal diagonal elements only. 1 minus lambda, 5 minus lambda, 1 minus lambda. So we can find, then what is the next step? To find the determinant of A minus lambda I. Directly we can find the determinant, but here was one shortcut method for third degree polynomial. So since it is a 3 cross 3 matrix, there will be it will be definitely third degree polynomial equation only. So first term you can write blindly as lambda cube minus sum of diagonal elements of A into lambda square plus sum of minus of diagonal elements of A into lambda minus determinant of A. So this is the formulation for 3 cross 3 matrix to find determinant of A minus lambda I. Directly also we can find. So this is one of the easiest method. So we can use this. Okay, lambda cube minus sum of diagonal elements. What are the diagonal elements? What are the diagonal elements here? 1, 5 and 1. So sum of diagonal elements is 1 plus 5 plus 1. So here I have represented 1 plus 5 plus 1 into lambda square. And for the sum of minors of diagonal elements of A. So we consider first diagonal element. What is the minor of first diagonal element? This is the minor of first diagonal element. So this is a minor of first diagonal element. 5 minus 1, that is 4. So when we consider the second principal diagonal element, when we consider the second principal diagonal element, what are the when we intersect row and when we intersect column and row for the 5, what are the remaining values? 1, 3, 3, 1 is the minor for the principal diagonal element 5. So 1, 3, 3, 1 means 1 into 1 minus 3 into 3, it will become minus 8. And for the last principal diagonal element, for a minor of last principal diagonal element, for minor of last principal diagonal element, this is a minor of last principal diagonal element. So 1 into 5 minus 1, that is 4. So 4 minus 8 plus 4 into lambda minus determinant. We know about the determinant. How to find the determinant we know. So determinant of A is 1 into 5 minus 1 minus 1 into 1 minus 3 plus 3 into 1 minus 15. So 3 into 14 is 42 here. I have represented the determinant here. So this is simplified as this equation is simplified as lambda cube minus 7 lambda square plus 36. So we found the determinant of A minus lambda I. And then we need to find the characteristic equation. Characteristic equation is nothing but determinant of A minus lambda I should be equated to 0. So here we have found the third degree polynomial. That third degree polynomial should be equated to 0 to find the eigenvalues lambda. Okay, to find 3 eigenvalues. Here, since it's a 3 cross 3 matrix, we will be having 3 eigenvalues. So, factorizing this equation, this will become lambda plus 2 into lambda square minus 9 lambda plus 18 equal to 0. Again, factorizing this second degree polynomial, lambda plus 2 into lambda minus 3, lambda minus 6 equal to 0. So, we found the values of lambda minus 2, 3 and 6. This minus 2, 3 and 6 are nothing but the eigenvalues of the given matrix A. So, hence we found eigenvalues of the 3 cross 3 matrix. So like that we can find the eigenvectors also for the same matrix. After finding the eigenvalues, for each eigenvalue we need to find the eigenvector. So first I will find for first lambda value, find the equations A minus lambda I into x equal to 0. I will find the equations for lambda equal to minus 2. Lambda equal to minus 2 means we can include in the principal diagonal elements. 1 minus 2, 5 minus 2, sorry, 1 minus 2, 1 minus of minus 2, 5 minus of minus 2, 1 minus of minus 2. Here I have represented in the principal diagonal elements. So this 313 171 313 x1 x2 x3 equal to 0. A minus lambda I into x equal to 0. So here we can represent in the equation form. First row, for the first row elements 3x1 plus x2 plus 3x3 equal to 0. And for the second row elements x1 plus 7x2 plus x3 equal to 0. And for the third row elements 3x1 plus x2 plus 3x3 equal to 0. We can solve the equations by any method. Here I am using cross multiplication method. This for lambda equal to minus 2. Here I am using cross multiplication method because this is the easiest one. I am taking first two equations to solve for the values of x1, x2 and x3. So for the cross multiplication, x1 by what are the other coefficients? If you want to find x1, what are the other coefficients? x2 coefficient and x3 coefficient 1, 3, 7, 1. So I have represented the coefficients here. And if we consider x2 coefficients means x3 and x1 should be considered. Coefficients of x3 and x1 should be considered. So 3, 3, 1, 1. And x3 by what are the other coefficients? 3, 1, 1, 7. I have represented here. So this is simplified as 1 into 1 minus 7 into 3, 3 into 1 minus 1 into 3, 3 into 7 minus 1 into 1. So simplified as x1 by 1 minus 21 minus 20, x1, x2 by 0, x3 by 20. So again we can cancel this value. This is minus 1 and this is 1. So eigenvector is minus 1, 0, 1 for the eigenvalue lambda equal to minus 2. For the eigenvalue lambda equal to minus 2. Hence we found the eigenvector for lambda equal to minus 2 only. So similarly for other eigenvalues also we can find the eigenvector. For the other eigenvalues lambda equal to 3 and for lambda equal to 6 we can form the equations like this. And we can take the first two equations And by cross multiplication method, here I have represented for lambda equal to 3 and for lambda equal to 6. Or by using cross multiplication method, these are for these equations, and for lambda equal to 6 by cross multiplication method. Here also same. This is simplified as x1 by minus 5, x2 by 5, x3 by minus 5, and for lambda equal to 6, this is simplified as x1 by 4, x2 by 8, x3 by 4. Again, this can we can cancel this. So this is minus 1, 1. Again, this is minus 1. And here also 1. And here also 2. This is 1. So hence the eigenvectors we found are x2 equal to minus 1, 1, minus 1 for lambda equal to 3, and x3 equal to 1, 2, 1, or the 1, 2, 1 is the eigenvector for lambda equal to 6. So we found 3 eigenvectors for 3 eigenvalues. So this is the method to find the eigenvalues and eigenvectors for any matrix. These properties are important to solve the gate problems, and also for other competitive examinations also these properties are important. So listen clearly. If A is a square matrix of order n cross n, it has the eigenvalues lambda 1, lambda 2 up to lambda n, then its transpose has the same eigenvalues. When A is a square matrix which has the eigenvalues lambda 1, lambda 2 up to lambda n, its transpose also has the same eigenvalues. For example, if we take 2 cross 2 matrix consists of the elements 4, 1, 3, 2, which has the eigenvalues lambda 1 equal to 1 and lambda 2 equal to 5, then its transpose. What is the transpose of the matrix? Here I am changing the rows and columns. So 4, 3, 1, 2 is the A transpose. This A transpose matrix also has the same eigenvalues 1 and 5. This is a property number 1. And then property number 2 is eigenvalues of a triangular matrix are just the principal diagonal elements of the matrix. So the matrix may be triangular, maybe upper triangular, maybe lower triangular matrix. If it is a triangular matrix means the eigenvalues of a matrix are just the principal diagonal elements. What are the principal diagonal elements in that? That are the eigenvalues of the respective matrix. So this is a representation for upper triangular matrix. This is a representation for upper triangular matrix because upper triangle has the elements. Others are zero value. Others are zero value. So this is a representation for the triangular matrix. This type of triangular matrix has the eigenvalues are same as the principal diagonal elements. These are the eigenvalues for the triangular matrix. Eigenvalues A11, A22 up to AN. Here, for example, I have written one matrix form. Here, this is upper triangular matrix. In the upper triangle only, we are having the values. In the lower triangle, we are having zero values. So, this is the upper triangular matrix. And here, we can find the eigenvalues directly. Eigenvalues are just the principal diagonal elements 1, 2, and 3. You can check it. Okay. And the next property is sum of the eigenvalues of a matrix equal to sum of the principal diagonal elements of the matrix. This is one of the important property. Sum of the eigenvalues of a matrix equal to sum of the principal diagonal elements of the matrix. Here I have taken the same example problem only. Already we found the eigenvalues as lambda I equal to minus 2, 3 and 6. Let me check this property. What are the principal diagonal elements? 1, 5 and 1. So 1 plus 5 plus 1. What is the answer? 7. Sum of the diagonal elements equal to 7. Let me sum the eigenvalues. Minus 2 plus 3 plus 6. This also 7. So it will be equal. Sum of eigenvalues of a matrix will be equal to sum of the principal diagonal elements of any matrix. The sum of the principal diagonal elements can be represented by the term trace. Trace of a matrix. Sum of the principal diagonal elements can be represented as trace. Hence, trace of a matrix can be defined as trace of A equal to summation of I equal to 1 to n aii, where aii are the principal diagonal elements. When I equal to 1, a11, I equal to 2, a22, I equal to 3, a33, like that. So, sum of principal diagonal elements is nothing but we can define that as trace of the matrix. And then next important property is product of the eigenvalues. Product of the eigenvalues, it is nothing but determinant of the given matrix. Product of the eigenvalues is equal to determinant of the matrix. I am taking the same example. What are the product of eigenvalues? Minus 2, 3 and 6 are the eigenvalues. Let me take the product. Product of the eigenvalues minus 2 into 3 into 6, that is minus 36. Let me take the determinant also for the eigenvalues. Determinant is also minus 36 only. Okay, so product of the eigenvalues will be equal to determinant of the matrix. These two properties are important to solve the problems. And then next property is, if the eigenvalues of a matrix are lambda 1, lambda 2 up to lambda n, it satisfies the following conditions. The matrix A inverse, if A has the eigenvalues lambda 1, lambda 2 up to lambda n, the matrix A inverse has the eigenvalues 1 by lambda 1, 1 by lambda 2 up to 1 by lambda n. Blindly we can calculate the eigenvalues if we are having the eigenvalues of A. And also matrix A square has the eigenvalues lambda 1 square, lambda 2 square up to lambda n square for A power n also. And matrix Ka, when a matrix is multiplied by the constant, its eigenvalues can also be multiplied by the constant term k lambda 1, k lambda 2 up to k lambda 1, k lambda n. And then matrix A plus Ki has the eigenvalues lambda 1 plus k, lambda 2 plus k up to lambda n plus k. And like that, A minus Ki has the eigenvalues lambda 1 minus k, lambda 2 minus k up to lambda n minus k. The eigenvalues of the idempotent matrix are either 0 or unit. Idempotent matrix can be defined as if A square equal to A. A square equal to A is the idempotent matrix formation. If A square is coming as A matrix, it is coming as the same matrix, then the matrix is said to be idempotent matrix. Such type of matrix has the eigenvalues 0, either 0 or 1 only. If X is an last property is, if X is an eigenvector of a matrix A corresponding to eigenvalue lambda, then Kx is also the eigenvector corresponding to the same eigenvalue lambda. For example, if the eigenvector is 1, 1, 1 for some eigenvalue means 2, 2, 2 is also, its scalar multiplication is also the eigenvector of the corresponding eigenvalue. 2, 2, 2, 3, 3, 3, 4, 4, 4, that also eigenvector for eigenvalue lambda. That is the meaning. So these are the properties of eigenvalues and eigenvectors. In the next lecture, we will solve the problems based on this. This is the channel Mani's Gate Tech Vision. This is a channel for engineering competitive examinations. You can subscribe to my channel, view the video lectures regularly. Thank you very much for watching the video.